Hello, my name is Marloes Mul and I'm an Associate Professor of Water Resources Management at IHE Delft Institute for Water Education. Today I'm going to talk about the water quality assurance and validation. An important aspect of the development of the WaPOR database is the internal and independent evaluations that are done to inform the improvements of the database. IHE Delft and the University of Twente are two institutions that have evaluated WaPOR data at different stages of the project, and they were instrumental in the improvements of the database. The different quality assessments evaluated the different WaPOR layers in various details. On the WaPOR website you will find the two reports describing the quality of the version 1 by IHE Delft and version 2 by the University of Twente. After the release of the version 3, IHE Delft will implement another quality assessment. In the earlier quality assessment of the WaPOR data, various approaches were undertaken to evaluate the quality of the data, and each has their own advantages and disadvantages. In both quality assessments, the most important evaluation is against observations. However, in absence of data, other approaches were also followed, including evaluating water balance closure from field to river basin scale, yield estimates, and CACOSTAT data, as well as comparing to other spatial data products, whether they are obtained from remote sensing, modeling, or reanalysis. Next to these common approaches, the evaluation of version 1 also implements plausibility checks from evaluating continental statistics and inspecting spatial patterns. The evaluation of version 2 also evaluated internal consistency checks and checks between levels. In this presentation, I will focus on the quantitative approaches. The quality assessment of version 1 evaluated all the different WaPOR layers using various approaches and different validation sets, as you can see in this table. From this presentation, I will focus on the main WaPOR datasets from climate, water, and land. The quality assessment of version 2, the focus was on detailed assessments of the reference ET, actual ET, and net primer production layers. For this presentation, I will not go into detail about the internal consistency checks of the layers nor the consistency checks between the different WaPOR layers, for which I refer you to the report. In the following sections, I will explain in more detail the different validations done for several of the WaPOR layers of version 1 and 2. The first layer to be evaluated was the reference ET layer. The comparison between the ground observation and the WaPOR reference layer is a comparison of a point to a pixel scale of 20 kilometers. The evaluation was done for two locations. This layer was also compared to two spatial data products, TerraClimate and GeoDAS. The evaluation against the point data provided very good comparison from both stations. For the comparison to the other products, significant differences were observed, with the WaPOR data providing more realistic values. The evaluation of version 2 evaluated the layer against more stations with varying results. For example, stations with taller vegetation appeared to perform less good, but also the same station performed low on evaluating the actual ET, which could be attributed to the quality of the station data. Considering the limitation of comparing the reference ET layer of 20 km resolution to point data, the results are very promising. After the release for version 2, the methodology to calculate reference ET data layer has been improved significantly. The precipitation layer was not the key focus of the validation efforts, as the data is derived from the CHIRPS database. The precipitation dataset was used to evaluate the actual ET data using a water balance approach. Based on the global evaluation of the CHIRPS data, the CHIRPS data shows very good results, considering the resolution of the data 5 kilometers and especially at large timescales. As CHIRPS uses observation data for bias correction, the decline in observation data is a concern. The actual ET data is the most extensive evaluated layer. For version 1, the data was compared at local scales by comparing to several eddy covariance towers and field soil water balance analysis. As you can see, the results vary significantly, with R-squared ranging between 0.1 and 0.72, and the bias ranging from -60% to +67%. The large-scale analysis showed better results. The comparison of the water balance for large river basins in Africa shows very good results, especially when comparing to other spatial data products. Comparison with SWOT model outcomes also shows very good results, with the main difference in the irrigated area, which WaPOR is able to pick up more accurately compared to the SWOT results. Version 2 was evaluated against more flux towers, again with varying results, as you can see here. The comparison using the water balance for major African basins for version 2 also shows very good comparisons with the general underestimation of the WaPOR-ET data compared to the water balance data. Finally, an example of the comparison to another spatial data product, in this case MODIS data, shows a wide cloud of points even for a specific land cover class like cropland, as you can see in the top graph. Comparing different land cover class statistics, you can see large differences, with WaPOR overestimating the MODIS data in almost all land cover classes. Generally, a good correlation is found except for bare land, flooded areas, and several forest land cover classes. The individual layers of the actual ET data was only evaluated for version 1 data, comparing the transpiration data to subflow measurements in Tunisia, as well as comparisons to 3 different spatial data products. With very little data to validate these different layers and uncertainty of the comparative products, the only indication it could be inferred is that the transpiration in cropland was underestimated. Several consistency checks were executed to indirectly evaluate these layers. Variance of different land cover classifications shows good patterns, with high transpiration over actual ET ratio for vegetative land use classes and low for bare land and open water. For irrigation schemes with known cropping patterns, the data shows good results for distinguishing irrigated versus non-irrigated areas. The results show that the patterns are consistent. The above ground biomass production layer of version 1 was evaluated against yield data in various locations. The biomass production was converted to yield using a number of crop-specific parameters as shown in this equation. The underlying net primary production layer was compared to 2 MODIS products. The results are very promising. An example for this Bwanji sugarcane production area in Ethiopia is shown here, with a range of yield similar to what is expected by the factory of 100 tons per hectare. The version 2 evaluation focused on the comparison with the station data, which shows varying results. For the evaluation against yield, the results also vary significantly. For example, the results for Bwanji are quite encouraging, but for the nearby Tahara, the results are not as good, with an underestimation of almost 50%. The comparison with the MODIS NPP data shows good results, but also across different climatic zones. The overall results show that the yield estimates are generally well within the expected ranges. However, stress factors affecting the harvest index or moisture content are not considered. WaPOR data is comparable to other spatial data products and shows realistic patterns. A reflection on the different validation approaches and results is presented here. Although the point comparison is preferred among the scientific community, but for evaluating continental products such as WaPOR, the number of stations is very limited to provide an accurate assessment of the entire dataset. In addition, the footprint of an ecovariance towers is generally not the same as the WaPOR resolution, and the quality of the EC tower data varies. When comparing to auxiliary data, the WaPOR data needs to be converted using selected parameters, which come with their own uncertainty. For the integrated comparison, the results are very good and comparative or better than other remote sensing products, but that doesn't necessarily mean the local data is accurate. Finally, the WaPOR team is preparing for an additional quality assessment of version 3. This quality assessment will focus on 2 parts. One is the evaluation of the input data compared to field observation, and specifically for the sharpened land surface temperature data, the data will be compared to high-resolution data. The second part will be the evaluation of the WaPOR data using similar approaches as discussed in this presentation. Thank you for listening.